Hello students. In this video we are going to discuss about some questions related to asynchronous counter as well as the flip-flops that we already discussed in the previous video. So you can see the questions one by one. The first question is explain the functioning of a master-slave JK flip-flop. So this is one of the important question related to the flip-flop. Here you have to explain how the master-slave flip-flop, JK flip-flop is constructed, what is the need of that master-slave JK flip-flop, and you have to explain the working, how it is working. So that's all about the master-slave JK flip-flop. Then the next question is differentiate SR and JK flip-flop. So say SR flip-flop, you have to explain its inputs, outputs, and its truth table, and what are the conditions that you will get. And in JK flip-flop also, we have to mention what are the important features of JK flip-flop and how you can obtain the different types of output based on the input that truth table. So you have to mention. So the next question is realize SR flip-flop using day flip-flop. This we already covered in the flip-flop video. So you can construct a different, that is you can convert one flip-flop to another flip-flop. That means you can obtain the function of another flip-flop. That is you can obtain the function of a day flip-flop using SR flip-flop, or you can obtain an SR flip-flop function using D flip-flop. That conversion also is very important related to the flip-flop. Next question is what is the race-run condition of a JK flip-flop, how it can be avoided. So race-run condition that occurs when J and K is equal to 1, that is toggle condition is occurring in JK flip-flop, and it is due to the propagation delay that you have to explain how it is taking place, and you have to draw the timing diagram also. Then you can just mention how it can be avoided. Basically, this is the answer of the first question. So the function of master-slave JK flip-flop. You can avoid the race-run condition using master-slave JK flip-flop. The next question is show how a T flip-flop can be converted into SR flip-flop. And this question is also something related to the third one, that is conversion of flip-flops. The next question is explain the operation of master-slave JK flip-flop. What is meant by race-run condition? This is the same as the first and third question, first and fourth question combined. So this is asked for usually for higher marks. Next question is with the help of a neat circuit and a timing diagram, explain the function of a DCT or decade asynchronous counter or a mode 10 counter. So when you answer this question, first you have to write the truth table of your mode 10 counter. So first one is truth table. So there you have to, since this is a mode 10 counter, you require at least 4 flip-flop in order to construct a mode 10 counter. But here it is not mentioned which type of flip-flop you have to use. So you can use either 0 or T based on the requirement. So here, since you require mode 10, you need a 4 flip-flop that is decided based on that condition. That means if you are using a 3 flip-flop, you can obtain only 8 states. But if you are using 4 flip-flop, you will get 16 states. So if you are using 4 flip-flop, you will get 16 states. So you need only 10 states. So after 10 states, you have to reset your flip-flop with the help of some gates. So we will be using an AND gate to reset your flip-flop when the 11th state is occurring. So here first thing is truth table. Then you have to draw the timing diagram of your mode 10 counter, as well as you have to draw the circuit diagram, and you have to explain its working. So this much thing you require to explain these questions. Now, this question I'm not explaining this mode turn counter because that thing we already discussed in the previous video. So you can just refer that video for mode 10 counter. It is nothing but decade counter. Next question is draw a 4-bit asynchronous up counter and discuss its characteristics. Draw the waveforms. Here also you have to first write the truth table, then draw the circuit diagram, then you have to draw the timing diagram also, then you have to explain the working. So this much things is required to answer this question. So again this for-bit asynchronous up counter is already discussed in the video related to asynchronous counters, so you can just go through that video. And here it is mentioned up counter, so you can directly draw the circuit that is discussed in that video. If suppose if that is down counter, you have to change the clocking signal. In up counter, we will be giving the clock signal of second flip-flop from the Q output of the first flip-flop, and down counter you have to change that to the Q bar. So that thing you can get from that video. Next is questions related to the shift registers. Here I can say the first question is design a 4-bit serial in parallel shift register and explain its working. There we have to draw the circuit of 4-bit parallel shift register and explain its working. So 4-bit means you have to use the 4 flip-flops, and here 4-bit serial in. So the data is fed serially, and the data is taken out parallelly. That means at the same time. Now this also explained in the shift register video. You can watch that video for that to answer that question. The next one is discuss different types of shift registers. There is this you have serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. So these 4 shift registers are there. So you have to explain briefly about these shift registers for that question. Now the last question is draw the parallel in, serial out shift register and explain. Similar to the first one, here the data is fed parallelly and the data is taken out serially. So in this shift register, these are the types of question that usually comes for the university. Next question is design a mode 11 asynchronous counter using T flip-flop and discuss its advantages. So here I have to design a mode 11 counter. So if you are using a 3 flip-flop, you can get only up to 8 states. If you are using a 4 flip-flop, you can get a state up to 16. So here you require 11 states, so you have to use 4 flip-flops. So when you are using 4 flip-flops, you will get a 16 state counter, but you need only 11 states. So after 11 state, you have to reset the flip-flop so that you will get the next state as 0, 0, 0, 0. So first we can write the truth table for this one. So if you are mentioning the output of 4 flip-flop as QA, QB, QZ, and QD. So 0, 0, 0, 0 is the first state, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So this is the truth table for the this mode 11 counter. Now you can now you have the truth table for the counter. You can just say that here you can have total 16 states are there, but for you need only 11 states. So I return only the 12 states. So starting from 000 to 1011. So this one is the 11th state. Now this is the 12th state. So once your counter reaches the 11th state, when it goes to 12th state, it should automatically reset so that your output will become 0000. That you can ensure with the help of a NAND gate. So here you can see that when 12th state is occurring, the output of QA, QB and QD is 1. So we can feed these three input to a NAND gate, and the output of NAND gate you can give to the low activated clear pin. So low activated clear pin means when the output is when the input is given as 0, that flip-flop get reset. So we will be giving the NAND gate input as QA, QB and QD. So QA, QB and QD, these three input outputs will be becoming equal to 1 only when the 12th state is occurring. That is never becoming equal to 1 before that state. So when these three inputs are 1 for the NAND gate, the output will be 0. So this output, 0 output, will be fed to the reset pin of your flip-flop. A circuit diagram for that mod 11 counter is shown here. Here you will take this QA, QB and QD, and that will be given to a NAND gate, and the output of NAND gate will be fed to the reset pin of each and every flip-flops. So once these three input, that is QD, QB and QA, becomes equal to 1, the output of your NAND gate will be 0, and that will trigger that will reset all the 4 flip-flops. So the state will become 0000. Then again, when the next clock pulse is coming, it will change the state to 0001, and this cycle will continue. So that is how you will design the mod 11 counter. Next question is design a 3-bit asynchronous counter using JK flip-flops. So 3-bit asynchronous counter, here I have to use 3 JK flip-flops, and we will be giving a JK pin of each 3 flip-flops as 1, so that you will get a toggling at each pulse that is coming to the clock terminal. Now the external clock is applied to the first flip-flop, and the second flip-flop is triggered with the help of with the Q in a terminal of the first flip-flop, and third flip-flop is triggered from the output of the second flip-flop. So here you have to draw the truth table first, then you have to draw the circuit diagram for 3-bit counter using JK flip-flop, then you have to draw the timing diagram. So here I will be using only 3 flip-flops because you require a 3-bit asynchronous counter. So here it is not mentioned up counter or down counter. So you can either draw the circuit diagram of an up counter and explain it, or you can draw the circuit diagram of a down counter and can explain it, since that is not mentioned in the question. The next one is what is a glitch? Show the timing diagram for a mod 6 asynchronous counter showing the glitches in the diagram. So here the glitch means it is the problem when you are using a or when you are designing a counter with a number of states, which is the power of 2. That means if you are using 2 flip-flops, you will get a 4th state. So if you are using 3 flip-flop, you will get 8 states. That means if you are using 2 flip-flop, you will get mode 4 counter, and if you are using 3 flip-flop, you will get a mode 8 counter. But you need a mode 6 counter, that is in between the states 4 and 8. So when you design a counter which has the state which is not the power of 2, or which is in between this power of 2, you have to check the output of your counter, and you have to check whether the required number of state is occurred, and when the next state is coming, you have to jump back to the first state. That is, in this case, if you are designing a mode 6 counter, 0 0 0 0 0 0 1 0 1 0 0 1 1 100101111 These are the states of a mode 8 counter, or when you are using a 3 flip-flops, these are the states that you will get. But here, this is the first state, this is second state, third, fourth, fifth, and this is the sixth state. So when the sixth state is occurring, and 3-bit flip-flop, 3-bit counter, the next state will be 110, but you require the state up to 101. Since you have to check whether the next state is occurring, that is when the 7th state is occurring. When the 7th state is occurring, you have to reset all the flip-flops. So this we will do with the help of a NAND gate. So here we will be using a NAND gate, where you will give the input as this one is QA, this is QB, and this is QZ. Suppose that is the name of your flip-flop that you give. Then in the 7th state, you can see that QZ and QB is becoming 1. So you will get QZ and QB to the input of an AND gate. So the output of this NAND gate will be 0 only when QC and QB is equal to 1. That is occurring only when the 7th state is coming. So when you give this NAND gate output to the reset pin of each flip-flop, when QC and QB becoming 1, the low activated reset pin of all the flip-flop is triggered. Right, so the flip-flop output will become 0. So you will get the first state. Now here you can see that the 6th state occurs 101. When the next clock pulse comes, the next state will come, or it will appear for a short duration. That duration depends on the propagation delay of your NAND gate. So when the state occurs, then after that the output of your NAND gate should be becoming 0. Then only your flip-flop gets triggered. So for a short duration, this state will be there. That means the 7th state will be there for a short duration, which depends on the propagation delay of your NAND gate. That is known as the glitch. That is known as the glitch. So this glitch occurs in this type of counter where the number of state is not equal to the power of 2. So here in this question, you have to mention what is a glitch first. Then you have to draw the timing diagram of the mode 6. So when you draw the mode 6 timing diagram, first you have to draw QA, QB, QC, and if you have to write the, or you have to draw the each state, and when the this 7th state is sorry 6th state is occurring, that is 1 0 1. So here it will be 1, here it will be 0, and this will be 1. Then when the next clock pulse comes, that is 101. When the next clock pulse comes, that is 110 is the state. So this will be remaining as 1, and this will become 1, and this will become 0. Then only this signal will be going to the NAND gate input. Then it will be jumping back to 0, 0. So for a short period of time, your output state will be 1 1 0. That means actually 1 0 1 is the sorry, 1 0 is state. Next state is 0 0 0. So actually the jumping should be from 101 to 000, but in between you will get a 110 state for a short period of time. So that's about the glitch and how you can draw the timing diagram for a mode 6 counter.